All right. Thank you. So I'm going to ask you to please get it together. So magnetism is the last part of this course. Um, First question everyone asks is this going to be on the test? No, this is not going to be on the test. Magnetism is the third part, which is going to be only tested on later quizzes and on the remember final exam is cumulative, just in case you forgot about that. Magnetism is tricky. It's not as mathematical as it was so far in this course. It's a little bit more conceptual based, and but the concepts are a bit more abstract, right? Because when you're talking about charges, you're talking about concrete, electrons, protons. But when we're talking about magnets, we're no longer talking so much about charges. We're talking about something called poles, and they just behave in a certain way. There's a something about poles that makes it seem a little bit more harder to grasp. There are some leaps of logic that we need to make, and we'll do them together. We'll see how it goes. It's one of the four fundamental forces of nature. You guys know them. You know one of them already. Is gravity. Second one is magnetism. Yeah, exactly. It's not electrostatic forces, all right, because we talked about that one in the second part of the first part of the course. Static electricity is not a part of the natural forces. This one is. You know what the other two are? Nuclear and strong one and the weak one. Yeah, strong one and the weak one. And they together they encompass nuclear forces and radioactive decay and things like that. We won't talk so much about them, but it's exciting because now we're talking about the second fundamental force of nature, and we're going to be, as you can imagine, drawing a parallel to gravity. But I also want you guys to draw a parallel to electric field. All right. And I drew this, or I didn't draw this diagram, but I'm showing you this diagram because it very clearly shows that parallel, right? So you have these three forces, yeah? I am. No? I try. Give me 1 second. Ah, that's my place. Okay, let's try NYB 03. I just opened up the wrong classroom. You got it? Instead of NYB 02, go to NYB 03. Does that work? Okay, perfect. So let me just minimize this. So I have these three fundamental forces, and or two out of the three fundamental are fundamental forces. But I want you to figure things out. So gravity is the force that acts on a mass, like electrostatic force acts on a charge, and so similarly, magnetic force acts on pole. All right, so we're going to have to get used to using this new term now, pole. All right, so you put a mass in a gravitational field, and you feel the force of gravity. You put a charge in an electric field, and you feel a force of electrostatic. And you put a pole in a magnetic field, you're going to feel magnetic force. Okay, that's what it says here. So far, so good. You guys remember doing the right-hand rule when you were in grade 10? Everyone's in the exam going like this, and there's that one poor kid going like this, and you're like, oh, that sucks. Everything is going to be wrong for that one. In fact, we're going to be using the right-hand rule for this section of the course. There are two right-hand rules and a left-hand rule. Yeah. I get to laugh because I suffered through all this. Now your turn to suffer. Magnets. Magnets are quite important. Everything that produces a sound through a speaker uses magnets. Your headphones, that tiny little thing, has a magnet inside because there's like a little tampon in there. And because of the magnet, it beats up and down. So you drive a current through your wire, right, and a current attracts the magnets and releases the magnet. So the magnet goes down, up, down, down, up, down, up, down, down. And that vibration of it carries this tampon, which is moving the air molecules really close to your ear, and that's making the sound. Did you guys construct? Did anyone do AST here in this class? Applied Science and Technology in grade 10? No? Or anyone, did they do the experiment in high school where you had to build a headphone or a speaker? No? Who did? Put up your hand. Okay, so you had a magnet and a solenoid, right? Yeah, and that's the principles behind the speaker. Anything that makes a sound, so telephones, computers, speakers, whatever, those things are all made of magnets. Most importantly, though, our electricity is made through magnets, right? So as you know, Hydro-Quebec is the one giving us electricity the most. We do get some nuclear energy, not so much, but we do get some. But Hydro-Quebec uses turbines to give our whole province. In fact, most of our country, and some of it is even exported, is coming from hydroelectricity. And the way it works is through solenoids. And what's happening is you're turning a turbine, and what that turbine is doing is it's a giant magnet at the middle of this, and there's a solenoid that you're turning the magnet around. And as you know, when the magnet turns around the solenoid, what you're doing is you're creating a current. All right, and that current is what's generating everything that we get access to. Okay? That current happens to be an AC current, and we're going to explain why it's an AC current. But essentially, that's how we get the electricity. It's as simple as an AC motor. Have you guys ever seen those little tiny motors that you can connect to like a circuit? It's like powers like a little powered airplane or something like that. Anyways, those things, instead of you giving its energy to turn, you turn it for it to give you energy. So it's kind of like the backwards of what you might have been used to. Anyways, we'll get there. If you're interested in this topic, look up these key terms. They're all very kind of complicated, but also very, very interesting subtopics of this unit, and quite a lot of interesting things come about if you look these things up. I don't have time for it. I don't have time for it, so I won't talk too much, but it's really more out of your own interest. I have my next slide, it's really long to load. There you go. All right, so here we're talking about the units of magnetic field. The magnetic field is measured in a unit called Tesla. All right, and a Tesla, you guys have heard of that, the car brand Tesla, yes? They're like super popular now. I never figured out the marketing strategy for Tesla. It's like a high-end hybrid, like, I don't know, it's just weird to me. What's important though is that a Tesla is the unit, and the symbol for magnetic field is B with an arrow over it. Okay. The magnetic field is a vector, similar to an electric field. It's symbolized by the letter B. It's measured in Tesla. There are other units for it. There are other units for it. I'm not going to get to it. One of the most popular ones are the Gausses, but getting it. So we're going to refer to them as Tesla in this. And there are different types of magnets, or things that produce magnetic fields. And one of them is going to be called a bar magnet. And this is the one that you're used to the most. So a bar magnet is any magnet that you've ever played with. All right? Have you guys seen those magnets that kind of look like a horseshoe? Like something like that? Yeah, it's got a north end and a south end, or a red end and a black end. Anyway, these are bar magnets, and they're considered to be permanent magnets. All right? What I mean by a permanent magnet is that they are always magnetized. Okay? So you can write that here. Permanent magnets are always magnetized. If I took a magnet, a strong magnet, and I had a whole bunch of paper clips, and I touched one paper clip, what's going to happen to that paper clip? It's going to what? it's going to stick with the other one. But is that paper clip on its own a magnet? No. So that's what I mean by permanent magnets and temporary magnets. All right, so that magnet itself is a permanent magnet. And what it does is that it magnetizes the paper clip, in which in turn magnetizes the next paper clip, and then you can get a string of paper clips going if your magnet is strong enough. The magnetic force is going to decrease each time. But the point is that you're using a magnet to create a magnet, and that's different from an object that's always a magnet. Okay. Our planet is a bar magnet. All right, so our planet has a permanent magnetic field. Just got really dark here on my screen. Our planet is a permanent bar magnet. We'll talk a little bit about that later. And what we need to know, though, is that magnets, they produce magnetic fields. All right. So yeah, I want to talk a little bit about convention. You guys remember what direction electric field lines go in? Positive to negative. Okay, so for magnets, it's also very easy. Magnetic field lines, they go from north to south. Okay, so here I have my north pole and my south pole of this magnet. And you can see that my field lines are going out of the north into the south. Okay. All right. So all magnets produce something called a magnetic field. And if I placed my finger there, where there's a magnetic field, is my finger going to feel a magnetic force? No, it's not. Why not? Yeah, because my finger is not a magnetizable object. All right, it cannot be polarized. I need to, if I were to place, let's say, an iron particle in there, would that be feeling a magnetic force? Yes, if I put iron filings there, it'll feel a strong magnetic force in the direction of the magnetic field. Okay. Remember how I mentioned how our planet is a magnet? I'm going to talk about that later. I thought there was a slide coming up. Back to those field lines, I just want to make sure that you guys understand that everywhere, so like if I have a magnet that's split up directly into two, so I have this one magnet, the south pole starts at exactly that moment, and then the north pole starts at exactly that moment. The magnetic field starts off right away. Okay, so it's not just at either opposite ends of the magnets that you have magnetic field lines. They're everywhere. So they start from there, they go towards the south. All right, and even in the middle here, they do the same thing. And this is represented by the direction a compass would take when you put it in the magnetic field. So if I were to put a compass here, where is the north going to be pointing? Down or up? Down. Exactly. The north would be pointing down on a compass, which is silly because it's pointing to the which pole? South pole, right? And so now we have to distinguish two things. We have magnetic poles and we have geographic poles. Okay? So don't get those two confused. They're totally different. We call them the North Pole and the South Pole. And then there's also the magnetic North Pole and the magnetic South Pole. We'll talk about them. So over here, this is a really classic example of bad information because this used to be published in a NASA website. And tell me if you noticed something wrong about this diagram. What about the field lines are on? What do you think, Leah? The arrows are not pointing in the right direction? The arrows are pointing in the right direction. Maxim. You mean these ones here? Oh, I see what you mean. Okay. It's not terrible. I mean, it is just a diagram, But there is some real concrete incorrect information here. Yeah. Exactly. All right. This says magnetic North Pole. That is totally wrong. Remember, a compass points towards the South Pole. All right. So that means a compass points towards the geographic north, but to the magnetic south. All right. So this here is wrong, and then therefore this here is wrong. And this is a very common mistake that you see in textbooks, and it's kind of silly because textbooks are meant to be the right answer to everything. So here it should say magnetic south. So I'm going to call it south sub S sub M, and this is going to be magnetic north, which is north sub M. It's very different, Andre. Come on. It's very different from the geographic north and the geographic south, just even in its position. Look how far they are from each other on the planet. All right, so we're talking about something that's not even in the Arctic anymore, right? I mean, it's kind of in the Arctic, but this would be the geographic North Pole, and our axis of rotation is around the geographic pole, right? But the magnetic north is somewhere pretty far away from it, considerably speaking. Okay, we're talking about hundreds of kilometers. Is that? Good question. No idea. Yeah. I'm not sure if it's Canadian or if it's in the in Russia. Yeah. We can look it up. I'm sure that answer is somewhere. So this is it. In reality, you have it so that the magnetic south is near the North Pole or the geographic North Pole. Okay. They're far from each other in terms of kilometers, but they kind of point in direction. Imagine that you're a Renaissance captain and someone who rides on a boat most of your time, and you have no real way of determining where is up, right? And this is a fantastic discovery to have something show you exactly which direction is quote unquote north, right? It's a very good point de repère that you can use to navigate yourself. I have a question for you guys. I have this compass, and this compass is placed next to an object that's charged, positively charged, in fact. Where is this compass going to go? Is the north going to be facing the positive? Is the south going to be facing the positive, or does it not move at all? Yeah? Why do you say that? Exactly. All right. You have to remember, it's not charges don't feel a force in a magnetic field. It's poles that feel a force in magnetic field. If the charges were moving, though, then that's a different situation, and we're going to talk about that. And that's called induction. We're going to talk about inductors, and yes, it's going to come back to circuits, and we'll have done full circle and come back to Gauss's law by the end of this, and everyone's going to be happy / really pissed off. So in this case, the answer is not at all, because there are no poles involved, right? So nothing is producing a magnetic field, therefore the compass doesn't move. Another question, if I had to have these three magnets, right, and they're picking up paper clips, which one of these situations is accurate? B, why? Yeah. So the principle is very similar to electrostatic forces. And so the answer, yes, is B. And that's because opposite poles attract. It sounds silly for me to tell you guys this, but you've never actually formally learned that opposite poles attract, right? Like when was it in school when we're like, north attracts south? Anyway, I thought I'd mention it just in case. Take 2 minutes to try some of these, okay? I'm going to do them at the same time. You guys do them in your notebook. Yeah.
Is there more of the left one or go to the one of the south one? The left one or no? Never.
Yes.
Okay.
It's going to be weak, but yes.
Yeah, okay.
Pick that up, please. He deserved it, but you can pick it up now. Yeah, for me. I didn't do it. Okay. Yeah. Pour le A, est-ce qu'il y en a qui sont comme quoi? What do you mean? Yeah. What's important here, you apply the same concepts as electric field. What I mean by that is that what's the main rule you have to follow when you're drawing electric field lines? They cannot cross. Yeah, that rule, yeah, it's important too. But no, they can't cross. Okay? Just like magnetic field lines cannot cross. The reason for that is because you can't have at a certain point magnetic field in two different directions. Okay? Simple as I talked to you guys about how the Earth is magnetic, and it's interesting how that is. All right. At the middle of the planet, it's a molten core. It's an iron core, and it's incredibly hot. And over the core is a mantle that keeps that temperature relatively cool. All right. So you have a humongous, the distance between here and here, you have a humongous insulator, right, creating a very big delta temperature in the core of the planet, right? So in this area here, there is a huge change in temperature, really hot here, really cold here, and so you have this convection. All right, you guys know what convection currents are? When something is a liquid or a gas is in contact with a very hot side and a very cold side, and then there's movement of the particles because of that change in temperature. It has to do with density and all sorts of other thermodynamic principles. Essentially, the liquid in the planet that's doing this is charged. All right, it's ferromagnetic, and it's a charged liquid moving. So, what do we know about charges that move? What do? They create a magnetic field. All right, and that's how our planet has a magnetic field. All right, because there are charges in our core that are in movement because of the convection. Okay. Our magnetic poles reverse every few years, right? Not in our lifetime, maybe, but they will reverse. And actually, every time they reverse, it takes less time for it to reverse the next time. Now, the first question that you might have is the humanity and all of the human organisms doomed to die when magnetic fields reverse? The answer to that is because it's happened so many times before, and we still have life on our planet, no problem. It hasn't happened within our recorded history, but it has happened within the history of intelligent organisms, or at least in primates, in terms of primates, okay? Now, how do we know this happened? Yeah. It's gradual, but it's not slow either. It's like it slowly happens, but over, let's say, a year or something like that. Yeah, I don't know the exact amount of time, but it's relative in terms of the planet's history. It's relatively fast. Okay, I don't know the exact speed though. It's not always. I mean, it's always being affected by other things, and I'm going to explain to you a little bit about what. Is in Canada? Oh, cool, awesome. I wanted to talk about, well, I mean, I don't have a slide for it actually, but I will just talk about it. Our planet has a magnetic field, and the fact that we have life on our planet depends on the fact that we have a magnetic field. What is the magnetic field of our planet providing us that allows us to have life? Sun's what? Sun particles? Not particles. You're close. It's protecting us from the sun. It's exactly. So the sun is frequently undergoing these things called solar flares, which emit a humongous amount of irradiation towards us. And we're protected from that irradiation because of our magnetic field. It doesn't allow it to penetrate us. But even that, even with our atmosphere that protects us against it as well, we still have harmful UVs that are entering our part of the atmosphere. So you still have to put sunblock. Like the magnetic field and the atmosphere isn't protecting us from everything, but it does protect against motion, and that's quite impressive that we have that. It extends about 400,000 kilometers outside of our planet, so it is quite big. If you were to imagine this as the magnetic field strength along inside our planet, does it make sense where the red regions are? Yeah, because they're near the poles, right? So near the poles, there's going to be, what is this? Someone's messaging stuff. Near the poles, it's going to be stronger, of course. Now look at the scale here. It says that it goes up until 60 microtesla. Microtesla is not strong, all right? So that we're really not affected by it. Anyone here had an MRI before? An MRI, magnetic resonance imaging. So when you're talking about doing an MRI, you go into a machine that's in the regular Tesla or even the kilo Tesla. You're talking about like thousands of Tesla, and obviously way stronger than the Earth's magnetic field. And yeah, it's not that harmful. It's actually one of the least invasive imaging techniques. Way better than CT scans, way better than X-rays, which is basically just one CT scan. And it's quite harmless. It's expensive and really noisy, and it takes a long time, but it's quite harmless. This is a model of the planet's poles being switched. You can see that they're in transition here, and the magnetic field lines are kind of twisted because the planet's magnetic field is switching. And lastly, just before I let you guys work on your circuits, there are some animals that that can sense the Earth's magnetic field. And you know that ducks migrate south, or whatever birds migrate south when when the winter is coming. Winter is coming.
Oh my God.
I had to say that. The birds migrate south Not because that's where they feel is warmer. That's not, they don't do that because they feel it's warmer, because they have in their, thank you. We had a moment. Moving on. Not because it's warmer. They don't feel that because it's warmer. They know which direction to go to because they have a system. They have a vestibular system that is made up of ferromagnetic liquid that responds to the earth field. So they know which direction to go to. So other than birds, there are some turtles and deer who do that. I mentioned this in this slide and to this slide. I'll let you guys read that. Circuits now. Here's what I want you guys to know how to do. Okay? Pay very careful attention, because if you ask me these questions, I won't answer them. Don't ask me questions I've already answered, please. You need to be able to use a multimeter to read resistance, capacitance, voltage, and amperage. Yep. Yep. You need to know how to use the device. Resistance, capacitance, voltage, and current. Okay? I might answer your question. Let me explain it. You do need to be able to build any kind of circuit, series circuit, parallel circuit, Wheatstone bridge, loop circuit, RC circuit, just a C circuit. You need to be able to build them, or at least recognize them. All right, you definitely need to build them, but recognize at least for sure all of them. You need to be able to do the calculations associated with all of these. Now, let's say I give you a Wheatstone bridge, ask you to find the unknown resistance, and I give you a multimeter. You should know where to plug in your multimeter in order to get the reading that you need to find the mystery resistor. Okay? You need to be able to calculate percent error. You need to be able to calculate percent difference, or at least know the difference between percent difference and percent error. You need to be able to recognize the parts of a circuit. You need to be able to use a color chart to determine what kind of resistors you're using. I'm not asking you to memorize them, right? You need to know how to calculate. An LED and a diode, you should know that they're both diodes. You should know how they work in a circuit and what they do and why you would use them. And you should also know, if it's not working, why. Okay? So for sure, I'm going to ask you a circuit question where I'm going to show you a circuit and say, why isn't this circuit working? Or what's wrong with this circuit? It might have to do with the battery being in the wrong direction, or I don't know. You guys figure that out. It could be a whole slew of things. Okay? Okay? That's fun? Yeah, I think it's fun. You're being sarcastic. I'm not being sarcastic. Why would I teach it if I don't think it's fun? All right. So I want you guys to be able to do that both with Wheatstone bridge, with breadboards, and with classical circuits using the wires. Okay. So go. You have access to everything, and you have access to. Go ahead.
For which measures do you have to put it into the other?
Once you're ready, I'll show you.